Welcome back to the Inclusive Mathematics PD series. In Module 4, we will discuss mathematical routines. These powerful routines are used for building number sense and declarative knowledge. By the end of this module, you will be able to describe important considerations for building declarative knowledge like math facts. You will have the opportunity to practice number talks like a student, using both invented and some real-life scenarios. You will also be able to identify a range of number sense routines that can be used across grade levels. In this module, we will focus on the foundation of our domain structure, helping students to develop declarative knowledge and number sense. I do want to point out that without our foundation, the structure can still stand. If students are not yet automatic and fluent with concepts, and they don't have a strong number sense, they can still engage in problem solving. That student might just need a little more support in that process. The foundation makes our structure stronger, making it easier to solve more complex problems. That's why we want to build it. Some students may have disabilities that directly impact their working memory, executive function, and processing speed. However, they can still grow their tower if we remember to have a dual emphasis on conceptual as well as procedural knowledge. When our structure topples is when we allow one pillar to grow faster than the other. This happens most often when teachers overemphasize memorizing procedural steps without ensuring the student understands the concepts behind those steps. Also, sometimes a parent may teach their child procedures they aren't developmentally ready for yet, and this may also make the structure lopsided and fragile. When this happens, we need to build in more scaffolding in our lessons. This may mean drawing pictures to go along with steps, integrating more manipulatives, and also engaging in daily routines to help students think about numbers. We can provide these scaffolds and routines to slowly help correct misconceptions and build a foundation that will make the student's structures stronger. Again, the base of our domain structure includes both number sense and declarative knowledge. Some students turn conceptual and procedural knowledge into declarative knowledge naturally, while some students may need more explicit practice and review. We are going to discuss some suggestions and considerations for helping explicitly build declarative knowledge. Remember, declarative knowledge is information the students retrieve from memory without hesitation, information that's memorized and recalled fluently. Declarative knowledge is often related to the development of number sense and functional math life skills, like related to money, time, and measurement. Just like any other domain of knowledge, you can use the explicit instruction model of I do, we do, you do to build declarative knowledge. Though I would not spend a large portion of your core math lessons emphasizing declarative knowledge, because many students will transform conceptual knowledge to declarative knowledge quite naturally, particularly when you use some of the number routines I will introduce shortly. For students who do not naturally convert conceptual knowledge to declarative knowledge, you can model the content, provide guided practice with immediate feedback, and then provide plenty of independent practice with opportunities for students to maintain those skills. If you choose explicit instruction for declarative knowledge, you should focus this content and introduce it sequentially. First, you should assess students' current level of knowledge through CBAs, like running records or timed probes. The purpose of doing a pre-assessment is to understand the baseline knowledge of the class as a whole, as well as individual student knowledge. You don't want to waste time drilling math facts they already know well. A pre-assessment also helps you know which facts are considered new and which are considered review for your instructional pattern. For example, if you're practicing fluently reading an analog clock, you'd start by just focusing on telling time to the nearest hour. Then you'd introduce time to the nearest half hour, then to the quarter hour, then to the nearest 5 minutes, and eventually to single minutes. Likewise, you wouldn't practice all multiplication facts at once. You might start with the ones and the identity property, then perhaps link to place value and the tens. Then maybe skip counting by fives or skip counting by twos. Then replicating that identity property with ones, now you could do that with tens and ones when practicing multiples of 11. When you get to those nines, you might want to consider some of the properties of multiples of 9, such as the digits of any multiple of 9 always add up to 9, or for larger numbers to some multiple of 9. If you look at the pattern of the ones digit as you progress through multiples of 9, you can see they are decreasing by 1. And if you look at the patterns of the tens digit, it is increasing by 1. In fact, the tens digit is always 1 less than the number you're multiplying by 9. So 9 times 6 always starts with 1 less than 6 in the tens place, 5. And then because the digits of any multiple of 9 add up to 9, I know 9 plus 6 must be 5 tens plus 4 to make 9, so 54. With 4s, you might think about doubling a number twice. I double for a 2, and then if you double it again, you get times 4. With 12s, you might think about hours, inches, dozens, and other real-life applications of multiples of 12. So for 12 times 5, I might think about how 5 feet tall is 60 inches. Or you might think about adding the multiples of 10 and 2 together. So for 12 times 8, I could think of 10 times 8, 80, plus 2 times 8, 16. Put those together, that gives us 96. When you introduce facts sequentially and link with number sense and conceptual understanding, you will find there really is not a lot left to memorize. The numbers left here on our multiplication table represent some of the facts students need to practice the most. Those tend to be those 6s, 7s, and 8s in particular. A common way teachers assess and practice math facts are with timed probes. You know what I'm talking about. These are usually those 1 or 2 minute timings that develop fluency at the independent practice level. This process usually involves using a probe sheet with a bunch of facts on them to time the student's speed and accuracy of responses in a set of declarative knowledge items. Some words of caution about timed probes, though. 1. Timed probes are not instruction. They are a form of assessment. Doing more probes will not help students get better with their math facts. 2. They often can cause a lot of unnecessary anxiety for students, particularly if you have the same goals set for each student and you make them compete with one another. If you do decide to use timed probes, you may want to consider not doing these in large groups and instead setting individualized rate goals rather than having the same goal for all students. If you are evaluating with writing, some students write slower than others. So if you think about it, it actually doesn't make any sense at all for students to have the same goal. Establishing individualized rate goals also helps reduce the stress on students, particularly if you don't conduct them in a competitive environment. One way you can calculate a good rate goal for fluency is to first see how many digits students can comfortably write in 1 minute. Have them sit calmly and don't have them rush. Have them copy down numbers on a list at a very calm, comfortable pace. Then, for younger students, a good fluency rate goal is about 50% of their writing rate. And for older students, around grades 4 and up, about 75% of their writing rate is considered a good rate goal. This should give students adequate processing time while also demonstrating some automaticity. These are not hard rules, just general rules of thumb if you're looking for some beginning expectations. Note, if you are evaluating knowledge orally instead of in writing, like with flashcards, you would first need to determine speaking rate, like how fast they can read numbers, rather than their writing rate, how fast they can write numbers. This would help you determine adequate rate goals. Remember, speaking rate for most students is typically faster than their writing rate. Now that we have covered explicit instruction of declarative knowledge, we are going to dive into some powerful routines for building fluency and number sense. Some of my favorite ways to help students develop declarative knowledge and number sense are to use games, both physical and virtual. Many math curriculums have games built right into them. When using prepackaged games, activities, and apps, you should evaluate them first for a few things. If students are playing a game without the presence of a teacher, you want to make sure the game provides some immediate affirmative and corrective feedback so they do not practice declarative knowledge incorrectly. Some commercial games often focus on a wide range of facts and skills instead of presenting content systematically and sequentially like you do in your instruction. They often contain distractors like pop-up ads or cute characters that do not actually enhance the math content. They also do not always allow for assessment. When students are practicing, ideally you want a way to record data about how well they did. It's your job to evaluate any materials you use and adapt them as needed to make the most effective practice opportunities for your students. Next, let's talk about general number sense routines. According to Gersten and Shard, number sense refers to a student's fluidity and flexibility with numbers. A student who has strong number sense has an understanding of what numbers mean, understands their relationships to one another, is able to perform mental math, understands symbolic representations, and can use those numbers in real-world situations. We focus a lot on number sense during preschool and early elementary years, but we know from research that number sense develops gradually over time. This development results from an exploration of numbers, visualizing numbers in a variety of contexts, and relating to numbers in different ways. In early elementary years, we help our students develop number sense related to counting, place value, quantity comparison, number symbol systems, number sequences, one-to-one correspondence, place value, and estimation. One thing you can do is ask students regularly to calculate mentally. Mental math encourages students to build on their knowledge about numbers and numerical relationships. When they cannot rely on memorized procedures or hold large quantities in their heads, students are forced to think more flexibly and efficiently and to consider alternate problem-solving strategies. We all develop synapses, or neural pathways in our brains all our lives. Even students with learning disabilities can stretch their cognitive abilities. We can give them some strategies for visualizing or ways of keeping track of information to help scaffold the process of mental calculation. Another common routine in early grades for developing number sense is called subitizing. This means seeing and recognizing numbers in sets without counting. There are so many great websites with subitizing activities. At the end of this presentation, I will link all of these resources on a Google Doc with a QR code. Let's look at an example of subitizing. Show students a group of dots or simple objects and ask them how many without counting them. Ask students to verbalize or share some way they saw the dots and how they knew how many without counting them one by one. A student may say, "There are 7. I see 3 over here and 4 over here, and I know that's 7. Another student may say, "I see 3, 3, and 1, and I know that's 7. There are all kinds of games you can play with subitizing, like bingo and dominoes, to have students practice seeing quantities without counting them one by one. 10 frames are another way of organizing quantities to help develop number sense. When you use 10 frames for addition or subtraction, try to have students determine sums without counting out every single dot. For example, in this 10 frame, someone with strong number sense would immediately recognize this as a quantity of 9, or 1 less than a complete 10 frame, without having to count every single dot. The great thing about subitizing is how it can expand to multiplication as well. Graham Fletcher has a wonderful website with subitizing for multiplication flashcards. These help students see equal groups. Number talks, short discussions on how to solve mental math problems or problems with multiple right approaches and answers, are a great way to help students verbalize their mental calculations and mathematical thinking. A number talk in kindergarten might involve you putting a number on the board and asking students to show different representations of that same quantity. As students get older, you may do more complex number talks. These are usually still mental exercises as much as possible. So students do not necessarily get out paper and pencils to solve problems like this during number talks. They would describe how they saw these numbers using mental math strategies. For example, in this problem, they may recognize that 4 and 6 make a 10, and then add that 10 with the other 4 tens to get 50 as the sum. By mid to late elementary school, you may stretch some mental math to also include some modeling or drawings. The key is to have problems or tasks that promote rich discourse and multiple right approaches and/or multiple right answers. In the case of this problem, students might draw an 8 by 9 rectangular room. Or they may draw an example like this. Both are correct. Here is another example. Take a moment to come up with 2 or 3 different values for what the blue bead could be worth. Explain your thinking, including what assumptions you made about this problem. Pause the video now and come back when you have at least one potential solution. What if I told you no 2 color beads could be worth the same value? Would that change your first response? What if I told you the orange and pink beads are worth the exact same value? What is one value for the blue bead now? Last one. What if I told you exactly 2 of the colors represent negative values? What could the blue bead be worth now? See how I added rules and considerations to make this more and more challenging? This is a great way to differentiate task-based activities like this to promote mathematical thinking and discourse. The Math Learning Center, which is part of the Bridges math curriculum, has some wonderful math-at-home resources and tasks that make great number talks or journal entries. The Would You Rather, What Comes Next, and Imposter tasks are brief, but really make students think and justify their responses. I encourage you to go and check some of these out. Steve Wyberney has amazing math resources on his website, including these SPLAT math talks that are a great introduction to algebraic thinking. In SPLATs, students have to figure out how many dots are hiding under the splat based on the number of dots they can see and the given total number of dots. Graham Fletcher is another one of my favorite math teachers who has so many free resources to create rich mathematical tasks. He has some great 3-act tasks on his website. 3-act tasks are groups of tasks that consist of 3 distinct parts. First, engaging and perplexing questions. Then, information seeking. And finally, solution discussion and revealing. Here's an example of a 3-act task. First, students had to estimate how many squares it would take to fill up the yellow rectangle on the floor in the hallway. In Act 2, the students worked together to observe, plan, and act. They aren't given enough of those tiles to simply count, but if they look closely at just one of the squares on the ground, they should be able to figure out the area for the entire yellow square. The final act of this 3-act task has the students come together and find out the answers together after discussion. There could even be a bonus 4th act with some extension tasks. Another powerful routine is making estimation an integral part of computing. Most of the math that we do every day, like deciding when to leave for school, how much paint to buy, what type of tip to leave in a restaurant, which line to get in at the grocery store, these all rely not only on mental math, but on estimation. However, traditional textbook rounding exercises don't provide the necessary context for students to understand estimation or building number sense. To do that, estimation must be embedded in problem situations. Providing reasonable estimation should be part of the problem-solving process on the regular. It also allows students to identify silly errors by noticing when one of their answers just doesn't make sense. Teachers should also question students about how they reason numerically. Asking students about their reasoning, both when they make mistakes and when they arrive at the correct answer, communicates to them that you value their ideas, that math is about reasoning, and most importantly, that math should make sense to them. Exploring reasoning is also extremely important for the teacher as a formative assessment tool. It helps them understand each student's strengths and weaknesses, their content knowledge, their reasoning strategies, and their misconceptions. Finally, talk about math across subjects. Children come to school with a stronger number sense when they talk a lot about numbers and problem solving regularly in their lives. So if you teach other subjects, like in history class, maybe you compare the number of soldiers on the north and south sides of the Civil War for different battles. Or maybe you present information in a graph or in a timeline. When learning about notes in music class, like whole notes, half notes, quarter notes, etc., make that connection to fractions. When learning to read Shakespeare, discuss the meaning of iambic pentameter. Talking about real-life situations and having students help you brainstorm is a great way to develop number sense at all ages. At the heart of all of these number sense activities and routines is the belief that all students can think mathematically. Allowing students to come up with their own creative mathematical ideas and solutions can be a powerful motivator in math. It can really help build a strong foundation for their mathematical learning. Now it's time for you to extend your knowledge on your own. All of the resources I mentioned throughout this module are hyperlinked on a single Google Doc, sorted by activity type. Follow the QR code to explore some on your own. Choose and practice routines as if you were a student, and also try some out with your class. Plan a debrief session with your colleagues and share your favorites and any tips for implementation.